In this video, we're going to discuss forces and Newton's three laws of motion. So let's start with Newton's first law. Newton's first law says that if there is no net force on an object, there is no acceleration. In other words, if there is an object that is moving, it will continue to move at the same velocity unless there is a net force acting on the object. If the object is not moving, it will continue to not move unless there is a net force acting on the object. Another way to say it is that if the velocity of something is changing, there is a net force on that object. Now, what is a force? Well, a force is what causes acceleration. It's what causes the velocity to change. Okay, that's a little bit circular, right? That if something accelerates, there's a force. And what's a force? A force is the thing that makes acceleration. Well, we'll get more intuition as to what a force is when we discuss the second law. But just for now, note that it has units of newtons. All right, so here's an example of using the first law to figure something out. A man is pushing a box across the floor at a constant velocity of 0.733 meters per second. He is pushing the box in the direction of the box's velocity with a force of 10 newtons. What is the force of friction on the box? Do we even have enough information to solve this? Well, there's the clue right there, constant velocity. So the box's velocity is not changing. That means by Newton's first law, there is no net force on the box. Well, wait, doesn't it say right here in the problem that there is a force on the box, that the man is pushing it with a force of 10 newtons? Yes, there are forces acting on the box, but in order for there to be no acceleration, for the velocity not to change, the net force has to be zero. So the sum of all of the forces has to be zero. So what forces are acting on the box? Well, we know the man is pushing it in the direction of its velocity. We'll call that the x direction. So there's a force of the man on the box. There must be some other force on the box that is canceling out that force such that there is no acceleration, such that the velocity is constant. And so that's the force of friction on the box. And so it must be in the opposite direction, and it must be equal in magnitude such that the box has a constant velocity, such that there is no acceleration. So the sum of these two forces must equal zero. It has to equal zero because if there was a net force, then the box would accelerate and its velocity would change. So we simply solve that. The force of friction on the box is equal to negative the force that the man puts on the box. So negative 10 newtons. So 10 newtons in the direction opposite its velocity. Now, if we have forces that go in different directions, we just write those forces as vectors, or we can add those forces together to get the net force just by adding vectors. So, for example, if I have forces Fa and Fb pointed in different directions, the net force is just the sum of the forces. So to add these forces together, I just take the vector that represents Fa, and then I take the vector that represents force B, and I put the beginning of that vector at the end of the of vector A, force A, and there's my sum. That's how I would add forces graphically. How do I do them algebraically? Well, what I'll do is I will break each of the forces up into its x and y components. So force A has an x component, force AX, and a y component, force AY. Now, when we do our diagrams, and then force B has an x and a y component. When we draw our diagrams and we're going to add all of our forces together, sometimes you may get confused and think that you've got extra forces, right? I've got FA, I've got FAY, and FAX, but FAY and FAX together make up FA, so I don't want to overcount. So sometimes it's a good idea just to put a little wiggly line through each of your forces after you have drawn the x and y components to remind you that those forces have already been taken into account by their x and y components. Then the x component of the net force is just the sum of the x components of the force, and the y component of the net force is just the y component of all the other forces added together. So the net force is, in this case, is just FAX plus FA plus FBX. There's a typo there. That should be B. FAX plus FBX in the X direction, and FAY plus FBY in the Y direction. So now let's do a problem that involves vectors. A man is pushing a box across the floor at a constant velocity of 0.733 meters per second. He is pushing the box downward at an angle of 23.3 degrees from horizontal with a force of 10 newtons. What is the force of friction on the box? So now we have our box, but the man is not pushing in the direction of the box's velocity. He's pushing downward at an angle theta. Well, we want to find friction. In order to find friction, we're going to use Newton's first law. There must be no net force on the box, otherwise the box would be accelerating. So the sum of the x components of the forces must be 0. Well, that means that the x component of the force of the man on the box plus the x component of the force of friction on the box should equal 0. Well, that means the x component of the force of the man on the box is just the magnitude of the force of the man on the box times cosine of theta, right? That's the x component of the force that the man is producing. And of course, the force of friction is entirely in the x direction. So now we can solve this for the force of friction on the box, and we find that the force of friction is negative 9.18 newtons in the x direction. But wait a minute. The friction has no y component, but the man is pushing with a y component. Does that mean that the box is accelerating in the y direction? Well, no, the ground is not going to let it accelerate in the y direction. So the sum of the forces in the y direction must equal 0. We're missing some forces here, right? So gravity, the force of the earth on the box. Gravity is pulling the box down. The man is pushing the box down. But of course, the ground is pushing the box up. We call the force of the ground pushing things upwards the normal force. So in order for the sum of the y components of force to be 0, that means that the y component of the force of the man on the box, plus the normal force, minus the force of gravity, minus meaning it's in the downward direction, must equal 0. All right, now Newton's second law says that force equals mass times acceleration. So this gives us some insight into what force is. Basically, force is something that makes things accelerate. All right, but the acceleration depends on the mass. So if I apply the same force to something with a bigger mass, there will be less acceleration. So the mass gives the object inertia. Inertia is the tendency to keep moving at the same velocity. And to overcome that inertia, we have to apply a force. All right? Now, of course, acceleration is the derivative of velocity with respect to time, and velocity is the derivative of position with respect to time, so that means that force is mass times the second derivative of position with respect to time. All right? Now, if the forces are vectors, that's okay, because acceleration is also a vector. So we can write the vector version of Newton's second law as such. So now, knowing that any mass in free fall will accelerate at g, what is the magnitude of the force due to gravity on a mass m? Well, the force is equal to mass times acceleration, but we know that the acceleration of an object falling under gravity is g, so we just replace acceleration with g, and that tells us the force of gravity near the surface of the Earth is just mass times g. So the force of gravity is proportional to the mass. So now let's use the information we found to solve a sort of complicated problem. Imagine I have a conical pendulum. So I've got a ball on a string, and it could, swing back and forth like a pendulum, but instead we have it going in a circle. It's like a pendulum where it's spinning around, making a horizontal circular motion. All right, so let's do a problem with our conical pendulum. A pendulum consisting of a ball connected to a string of length L is making a circle of radius r. If L equals 80 centimeters and r equals 20 centimeters, what is the time it takes for the ball to make one revolution? Is that even enough information to figure that out? They seem quite disconnected. Well, let's use physics and math, and we can solve this. So we're going to use the Snuggly Dog method on this one. So first, we're going to start off with a diagram. So here is my ball on a string. Its string has a length r, and the ball is making a horizontal motion. It's spinning. It's going in a circle horizontally with a radius r. Now, what are the forces acting on the ball? Well, the string is pulling on it with tension. We'll call it force of the string on the ball. And then gravity is pulling it downward, force earth on the ball. Okay? Now, if the ball is going in a horizontal circle, we've already studied things going in circles at a constant velocity, and we know that there is a relationship between the acceleration and the velocity of something going in a circle at constant velocity, going in uniform circular motion. And we know that the direction of the acceleration is towards the center of the circle. So we know that the acceleration is towards the center of the circle. All right, it's this way. And we'll label the angle of the string with theta. That will help us to work our math problems. Okay, now our objective is to find the time for one circle, for one oscillation, one time around the circle. The givens. We're given that gravity is 9.81 meters per second squared. We're given the length of the string, and we're given the radius of the circle that the ball is making. So, our basic equations. First of all, velocity is distance per unit time. So if I can find the velocity of the ball, and I know the distance that it travels as it goes around its circle, I can find the time it takes to go around the circle once. Well, of course, the distance that the ball travels as it goes around the circle is just the circumference of the circle, 2 pi r. And I also know that for an object going in uniform circular motion, the acceleration is equal to the velocity squared over r. So if I do the acceleration, I could find the velocity that I could plug into that equation to find the time. Well, how do I find the acceleration? Well, force equals mass times acceleration. And of course, the force due to gravity is just mg. So now, once again, here's our diagram for the problem. Let's do our symbolic solution. So we're going to start right here by saying, well, look, if we need the velocity to plug into this equation, so let's solve our acceleration equation for velocity. And when I do that, I just get velocity is equal to the square root of a times r. And then, of course, I can solve this equation for time. The time that it's going to take to do one circle is just the distance, 2 pi r, divided by the velocity. And I've solved this equation for velocity, so the time is just 2 pi r over the square root of acceleration times r, which is 2 pi times the square root of r over acceleration. So now I just need to know the magnitude of that acceleration, and I can find the time. How am I going to find the magnitude of that acceleration? Well, F equals ma, and so what we're trying to find is the x component of the force. The x component of the force is just mass times acceleration, right? Because the acceleration is in the x direction. So that means that, well, what is the x component of the force? Gravity has no x component, so it's just the x component of the force due to the spring, of the string. So mass times acceleration is the force of the string on the ball, the x component of that. And the x component is the force of the string on the ball times sine of theta. Okay, so there we go. Acceleration is just the force of the string on the ball times sine of theta over m. But what is the force of the string on the ball? We're not given that. Well, we know that the net force in the y direction must equal 0. The force in the y direction is equal to the y component of the force of the string on the ball plus the y component of gravity, the force of the earth on the ball. Well, the force of the y component of the force of the string on the ball is just the force of the string on the ball times cosine of theta, and the force due to gravity is just negative mg. It's mg in the negative y direction. So we can solve this, and now I know what the force of the string on the ball is because its y component is just big enough to cancel gravity such that there is no y component of acceleration. So we found that the acceleration is the force of the string on the ball over m times sine of theta, and we found that the force of the string on the ball is just mg over cosine of theta. We put them together, the m's cancel out, and this just becomes g tangent of theta. So the acceleration then is just g times the tangent of theta, of course, is just r divided by, that's the opposite side, divided by the adjacent side, and the adjacent side we can find using the Pythagorean theorem, and it's just the square root of L squared minus R squared. All right, now we have the acceleration, we can plug that into our equation for the time. So we plug that in, and we simplify, and there's our answer. All right, so step N is to plug numbers in. When we plug numbers in, and we find 1.77 seconds. Our units, we check the units. It's just meter squared minus meter squared to the 1/4 over the square root of meters per second squared. So that's good. We can subtract meter squared, take meter squared to the 1/4, and that's the square root of meter squared. 1 over the square root of second squared is seconds, and it all works out. Our units work. We get units of seconds. Gauge and guesstimate. Well, you can imagine you're swinging, you have your, your headphones on a string and you swing it or whatever, something of reasonable size that you might swing with your hand, you kind of expect on the order of a second, right? It shouldn't take a minute to do a revolution. It shouldn't take a millisecond. So it seems realistic that, the answer that we got. Now, here is the symbolic form of the answer we got. So we can use step L, limits, trends, known cases. We know that if g increases, the time should decrease, right? If gravity's pulling harder, then it's got to go faster, right? The force in the string has to be bigger. The tension in the string, that means it's got to go around faster. And that's what we see as g increases, t should decrease. Also, what would happen if r equals L? So I'm swinging this thing so fast that it's moving perfectly horizontally. All right, that means that in order to do that, I've got to spin it infinitely fast, right? Because that means that the y component of the string is 0 and it cancels gravity, right? So the y component times sine of theta, when theta is 90 degrees, is equal to gravity. What can I multiply by 0 and get something that cancels gravity? It has to be infinite. All right, so that would be an infinite force, 0 time to go around the circle. So, right, that's an unrealistic limit, but it's a limit we can use to check and see if our answer behaves correctly. All right, and then why? Yes, we did do this ourselves. All right, now Newton's third law says equal and opposite forces. If one thing pushes on another with a given force, that other thing is also pushing back on the first object with the same magnitude of force but in the opposite direction. All right? So, you jump up in the air and the earth pulls you down, the force of gravity. The earth pulls you down, but you pull back on the earth with an equal and opposite force. The earth is being pulled upward with the same magnitude of force that the earth is pulling you downward. Now, you don't notice it because the earth has so much mass, right? And F equals ma. So even though the force that you pull on the earth with is exactly the same as the force in magnitude as the force that the earth pulls on you, the earth just doesn't move much because you divide the force by the mass, you get very tiny acceleration. All right, you're standing on the floor, and because of gravity, you're pushing on the floor, and the floor pushes back the same amount. So again, the force of the earth on you is negative mg. It's an acceleration downward. But you are pulling the earth upward with a force of you on the earth of positive mg, equal and opposite forces. You are pushing down on the floor. The force of, the floor is holding you up, right? It's pushing up with a force mg to hold you up. So the force of the floor on you is mg, but the force of you on the floor is negative mg. All right, so that's what Newton's third law says, equal and opposite forces. So here's a problem we can work with the third law. Arthur and Trillian were standing still on a slab of ice. Then Arthur pushed Trillian on the back with a constant force for 1 second. As a result, Trillian is now sliding forward at a speed of 0.731 meters per second. what is the direction and speed that Arthur is now going? Assume that the ice has no friction, that Trillian weighs 70.2 kilograms, and that Arthur weighs 95.1 kilograms. All right, so how do we work this problem? Well, Arthur's velocity is just the acceleration of Arthur times time. And we can find Arthur's acceleration because the acceleration of Arthur times Arthur's mass is just the force acting on him, the force of Trillian on Arthur, right? And so the acceleration of Arthur is just the force of Trillian acting on Arthur divided by Arthur's mass. So his velocity is just the acceleration, which is the force of Trillian on Arthur divided by Arthur's mass times the time that that force was applied. Well, that's great because we want to know Arthur's velocity and we know Arthur's mass, but we don't know the force that Trillian applied to Arthur, right? That's Arthur's pushing on Trillian, and so Newton's third law says that Trillian is pushing back on Arthur, right? But we don't know how big that force is, the force of Trillian on Arthur, and we don't know the time. But what we do know by Newton's third law is that the force of Trillian on Arthur is just negative the force of Arthur on Trillian. So when Arthur pushed on Trillian, Newton's third law says Trillian's pushing back on Arthur. Okay, so that's great because Arthur was pushing Trillian, but I didn't tell you in the problem how hard Arthur pushed. I didn't tell you what force, and I didn't tell you how long. I just said it was a constant force for a given time. Well, the force of Arthur on Trillian is equal to the mass of Trillian times Trillian's acceleration, and Trillian's velocity is just the acceleration times t. So that tells me that the acceleration of Trillian is just the final velocity of Trillian divided by the time that that force was applied. And then I can plug that into Newton's second law and find that the force of Arthur on Trillian is the mass of Trillian times the velocity of Trillian divided by time. So now we know the final velocity of Trillian, we know her mass, we don't know the time that we do know the time that Arthur pushed, so I can go ahead and plug that into this equation up here. So I know that the velocity of Arthur is negative the force of Arthur on Trillian divided by the mass of Arthur times time, right? It's the force of Arthur times Arthur on Trillian, because negative the force of Arthur on Trillian is the force of Trillian on Arthur. And I know the force of Arthur on Trillian because I got that from her final velocity. So we plug that in, we plug this into this equation and simplify things, and we find, the velocity of Trillian, negative velocity of Trillian times the mass of Trillian divided the mass of Arthur will give us the velocity of Arthur. So we didn't even end up needing to know how long Arthur was applying this constant force because in the end it canceled out. So we plug the numbers in and we find that Arthur is moving at 0.540 meters per second. I'd lost the minus sign, in the opposite direction as Trillian. That's the end of our video.